In this lecture, we'll discuss on the vector fields for one-dimensional systems, and we'll try to get an idea of what a stable equilibrium point and what an unstable equilibrium point means for these systems. And this will also give you an idea in general what it would essentially mean. Okay, so let's say that we have this autonomous system where f is mapping from reals to reals, okay, and x of t also belongs to real. So let us say that f of x is x squared, which essentially means x dot is x squared. This is the system that we are considering for this particular example. Okay, so the vector field here in this case, I mean, because this is a single dimensional system, you need to set up only one axis to represent this single state, and the vector field will be all along that axis. Okay, so if you let's say this is the axis that I have set up, over which I want to show how the vectors will look like, and suppose this point here is the origin, which is x equal to 0 point. Okay, and then we have 1, 2 and 3. Similarly, -1, -2 and -3. Okay, now you see here that at x equal to 0, the vector that is associated with it is 0. At x equal to 1, the vector is, I mean, x dot is going to be 1, right? So you start at 1, and let's say this length of vector represents 1 unit for the f of x vector. So this is 1. You start at x equal to -1. So in this case, x dot is still 1. Okay, which means it will start at -1, and this will be the vector that you have associated at -1. Next, you go to x equal to 2. At x equal to 2, x dot is 4, and the vector here will start at 2, and let's say this is what the vector 4 would have the length. Similarly, at x equal to -2, x dot would be 4, so it starts here and will look something of this sort. Now when you go to x dot x equal to 3, so x dot is 9. So this is the vector that you have, and at -3, this is the vector that you have, right? So what you observe here is whatever is the value of x, the vector is just the square of the value, with the vector starting at the point where fx has been evaluated. Okay, so if you draw this for the entire all points on the real axis, you'll get the vector field for this one-dimensional system. Okay, now from this vector field diagram, you observe that at 0, x dot is 0, so 0 here is our equilibrium point. Okay, this is the equilibrium point. So if the system starts at 0, so if the initial condition is such that x of 0 is 0, then the system will always stay there. Okay. Now suppose the system starts slightly to the left of 0, which is on the negative side. So let's say x of 0 is equal to -5. Okay. If x of 0 is -5, then what you see is x dot will be such that it generates a positive vector, which means -5 will increase. It will increase and let's say go towards -4, and then -4, at -4 you x dot is 16, so it will further increase and it will again let's say go towards -3, and again at -3 it is x dot is 9, so it increases. So what you see is the solution progresses in this direction because x dot is positive for negative values of x, which means x is going to increase. But also notice that as the value of x increases when it is negative, the magnitude of x keeps on decreasing, and hence the magnitude of x dot also keeps on decreasing. So by the time your value of x is -1, the magnitude of x has reduced to 1, and hence x dot is also 1 in this particular case. Okay, so if you go to any value beyond 1, what you see is the x dot value reduces even further. Okay, so the system evolves slower and slower as you approach closer and closer to the origin. Okay, and when you are closer to origin, very close to origin, x dot is also very close to 0. Okay, so the system evolves fast when it is far away from the origin. It slows down and as it approaches towards the origin, and it is very slow very where it is arbitrarily close to origin, but it is never going to cross origin. So what will happen is, for this initial condition of -5, the solution will grow and go towards 0. Okay, from anywhere on the left, from sorry, -5. Now the same holds for any point on the left side of 0. Basically, if the initial condition is negative, then the solution will evolve towards 0. Okay, so it will go and try to settle at 0. So what you observe is, if the system is already at 0 and someone disturbs the system from this equilibrium point, so someone, let's say, comes and disturbs the system so that the system attains a negative value. Okay, meaning x of 0 is negative. So let's say x of 0 is -0.1. In this case, the system will have a tendency of going back towards the equilibrium point 0. Okay, now observe the right hand side of the 0. What happens? As let's say that you start at some point very close, or some point close to 0. Let's say you start at 0.1. So we start at x of 0 is equal to 0.1. What is x dot in this case? It is 0.01. The positive value is less, but it is positive, and the initial condition is also positive. So what it means, with x being positive and x dot being a positive value, it indicates that x will grow. So starting at 0.1 with a growth rate of 0.0, with growth of 0.01, you essentially see an increase in the value. So with this increase, what will happen is it will reach 1, and at 1 x dot is equal to 1, so it will grow even faster and will reach pass through 2, and at 2 the x dot is 4, so it is even faster, and so on. So what is happening is, you started at 0.1 and the solution keeps on moving away from this equilibrium point 0 at a faster rate. So the rate at which it keeps on moving away from the equilibrium point increases as the distance between the equilibrium point and the points on the solution trajectory keep on increasing. Okay, so what happens is if the system is at the equilibrium point 0 and someone perturbs the system so that x of 0 attains a positive value, then the solution trajectory will move away from the origin. The system will not have a tendency to evolve such that the states evolve towards the origin. It won't do that. Okay, the states will evolve away from the origin. So in one direction of perturbation, which is perturbation towards pushing the system towards the left, the system is behaving at the equilibrium point, is behaving as an attractor. It is trying to attract the system back. But if the perturbation is towards the right of the equilibrium point, so if the system is pushed towards the right of the equilibrium point, then the equilibrium point is behaving kind of a repulsor. So the solution trajectories are moving away from it, right? So such a equilibrium point is classified as a unstable equilibrium point. In fact, from the vector field, mm, oh no, so this is an unstable equilibrium point that you have. Now what will happen if, let's take another system where uh, f of x is, let's say, minus of x cubed. Okay, let's say this is what we want to study. So you have the axis for the state x set up like this. This is again a one-dimensional system. Let's say the 0 is over here. This is 1, 2, 3. This is -1, -2, and -3. This is what we have, the points. Now let's see what happens. At x equal to 0, x dot is 0. Right? So 0 is the equilibrium point. At x equal to 1, x dot is -1. So the vector here is going to be this. At x equal to 2, x dot is -8. Let's say the vector is going to be this. This is roughly giving you an idea of how the magnitude is going to look like. This is not up to the scale, okay, but at least gives you an idea of what is going to happen. And then at x equal to 3, minus x cube is going to be 27. So this is what is the vector that you have. Similarly, at x equal to -1, x dot is going to be 1. At x equal to -2, x dot will be 8. And at x equal to -3, x dot will be 27. Okay. Now, from the vector field drawn, we can predict how the solution is going to evolve given an initial condition. Okay. So let's say the initial condition here is that interests us is x of 0 to be -3. Now at x of 0 to be, when you start at -3, your x dot that you will have is 27, which is a positive value. That essentially indicates that -3 is going to grow. Let's say that it grows and grows till x equal to -2. At -2 again, x dot is 8, so it will further grow. But observe that the rate at which the system will grow is slower when it was at -3 as compared to when it was at 2. Okay, system is faster at -3, and as it progresses towards -2, the rate at which it is growing will also decrease. The magnitude decreases, but the value increases. Okay, in this particular case. Now, as it evolves, it reaches -1, and at -1, x dot is 1, so it will further evolve. So it will keep on evolving while the magnitude of x dot keeps on dropping, and finally at 0 my x dot will be 0. Okay, so you keep on evolving towards 0 when you start on the left side of 0, which means if the system was already on the equilibrium point and someone disturbed the system or someone perturbed the system so that the system moves to the left of the equilibrium point 0, and then you remove your perturbation force, then the system will have a tendency of going towards the evolving towards the equilibrium point itself. Okay, now observe for points on the right side of 0. Let's say that here you start at x of 0 equal to 3. You will observe a similar thing happening in this particular case as to what happened for x of 0 equal to -3 as the initial condition, except for everything is now reversed in terms of the evolution. So here, as at 3 x dot is -27, so the value of x decreases and it will reach 2, and once it reaches 2, x dot is -4, so it will further decrease and it again reach 1, and at 1 the value is -1, so it further decreases. So this is what happens. Okay, so what you are observing is if you start on the right hand side of 0, the value keeps on the value of x keeps on decreasing as time progresses, and finally it is approaching towards 0. Okay, so if the system is at equilibrium point and someone perturbs the system so that the system comes to lie on any point on the right hand side of 0, and once the perturbation force is removed, the system will actually have a tendency to move towards the equilibrium point. So in one-dimensional cases, there are only two directions in which the system can be perturbed, and in both the directions, we are seeing that the solution has a tendency to move towards the equilibrium point, which is 0 in this particular case, and hence we classify such equilibrium points as stable equilibrium points. Okay, so to put up a very informal definition, or to put up some these in statement for stable equilibrium points, we can say that for all perturbations on the system around the equilibrium point, for all perturbations on the system leading it to initial conditions around the equilibrium point, the solution trajectory evolves towards the equilibrium point. So in all possible directions, if you perturb the system and leave the perturbation there, then wherever you leave the perturbation, that serves as the initial condition now, and from there you will see that the solution trajectory, which is basically how the states that they evolve, are actually going towards the stable, towards the equilibrium point. Okay, then it is called as stable. If this is not satisfied, then it is known as unstable. So unstable equilibrium points are basically um, so unstable equilibrium point are basically there exist some perturbations leading to initial conditions such that the solution trajectory do not come back to the equilibrium point and move away from it. So they will not come back to the equilibrium point, but instead they move away from it. Okay. So these are known as the unstable equilibrium points. If you have a tendency of moving towards the equilibrium point or do not have a tendency to move away from the equilibrium point, then you classify it as stable. But if it has a tendency to not only a tendency of not coming back to the equilibrium point and also to move away from the equilibrium point, then we classify it as a unstable uh, equilibrium point. Okay, let us take one more example. Fx is x minus 3, x minus 9. Okay. So if you plot x versus fx, then what you get is a trajectory that looks like this, roughly like this. This will be 3 and this point will be 9, with this being the 0. This is where the x equal to 0 lies and fx equal to 0 lies. Okay. Now, so this basically serves as the origin for the xfx axis. So using this information, we can sketch the vector field. So this is the origin. Let's say this is 3 and this is 9. So clearly at 3 and at 9 f of x is 0. So f of 3 is 0 and f of 9 is also 0, which means x dot is 0 at x equal to 3 and x equal to 9. So both of them are essentially equilibrium points. Okay, now you observe how fx changes as the value of x changes. For every point to the left of 3, okay, for every point to the left of 3, f of x is positive, which means x dot is positive. Okay, so the arrows that you will have or the vectors that you will have at points to the left of 3 will always be pointing towards the right side. So for example, if you choose a point here, the arrow here is likely going to point like this. Okay, I'll not be peculiar about the magnitude in this particular example. What I am interested in is looking for the stability and instability of the equilibrium points 3 and 9 to classify them as stable or unstable. So I'll just be interested in the direction in which the arrows are going to look, because that is what is going to give me an idea of how the solution is going to evolve. Okay, and also you can observe that farther away from 3, higher is the magnitude of x dot, and as you come closer and closer to 3, the magnitude of x dot falls, and at 3 x dot is 0. Okay, so if you are farther away from 3, you have a tendency of moving at a faster rate, and as you come closer to 3, the rate at which you evolve slows down. Okay, but you'll never cross 3. So at any point that you take on the left hand side, the arrows are going to point towards the right. So roughly the vector field diagram is going to look like this, with the length of the arrows reducing and finally going to 0 at 3. What happens to the points between 3 and 9? The points between 3 and 9, for those, f of x takes a negative value. So x dot is negative, which means for any point that you choose between 3 and 9, the the arrows will actually point towards left. Okay, so point towards 3. All the arrows will point towards 3. And also you observe this, points which are closer to either 3 or 9, the magnitude of fx is low, but as they move uh, away from 3 and as they are somewhere in between 3 and 9, the magnitude is highest there. So if you are starting close to 9, then the rate will be very low, and as it moves away from 9, the rate increases, and then as you come closer to 3, the rate further drops. Okay, so here the arrows would be small. Of course, at 9 the arrow length is 0, because 9 is a equilibrium point. So the magnitude increases, and then again the magnitude drops as it moves towards 3. Okay, so this is what we have. Now all points to the right side of 9, f of x is positive, indicating the arrows will again point towards the right side, with magnitude being smaller when you are close to 9, and as you move away from the 9, magnitude increases. So this is the rough sketch of the vector field that we have for the one-dimensional system that we have in hand. Okay, so now you observe this. For any point that you start on the left of 3, the solution trajectory will evolve and the system will try to go towards x equal to 3. And for points towards the right of 3 but to the left of 9, so all points between 3 and 9, if the system starts in that range, if the system is such that the initial condition lies between 3 and 9, then again the system will have a tendency to move towards the equilibrium point 3. So what you see is with equilibrium point x equal to 3 under consideration, the two directions that you have, in both the directions, the system has a tendency to move towards equilibrium point 3, and hence we classify this system, this equilibrium point, as a stable equilibrium point. Now observe the equilibrium point 9. If you are not on the equilibrium point 9 but slightly off from the equilibrium point 9, then the solution has a tendency of moving away from x equal to 9. Okay, in both the directions, not just one direction which you had seen in the previous example, the first example that you had seen, but in this case it actually moves away in both the directions from x equal to 9, which is the equilibrium point under consideration, and hence this equilibrium point is classified as a unstable equilibrium point. Okay, so this rough idea of the vector field for the one dimensional system is not only helping us in identifying what the equilibrium points are, but also helps us in identifying whether the equilibrium points would be stable or unstable. Okay, so um, I leave you with one question for again a single dimensional case, which you can possibly take up as one of the assignments. Is if you had x dot equal to f of x and f of x is sine of x, then for this is again a scalar, sorry, it's a one dimensional system. Most books you will find this to be called as a scalar system, not a vector system. um, Try to find out the equilibrium points and sketch the vector field for the same. So find out the equilibrium points, sketch the vector field, a rough idea that will basically be able to tell you what the equilibrium points are, and it will be able, and you should be able to say which equilibrium points are stable and which equilibrium points are unstable. Okay, so we'll stop here. Thank you.